Yes, you're audible.
Okay. Should we wait for some time? Let other people join, or can we start?
Yeah, let's wait for like 5 minutes and then you can start.
Okay. Let's wait till 11. Okay.
Okay.
Yeah, Avinav will start now.
Yeah, shall we start?
So, hello, good morning, everyone.
Yeah, maybe I'll introduce you first and then you can start. Daibik.
Yeah, okay.
Okay. Okay, good morning, everyone. Welcome to the fourth day of the Limit Online Camp. Today we have with us Daibik. He just completed his B.Math from ISI Bangalore and he'll be speaking on the topic how to lose by making the best decision. So yeah, over to you, David.
Okay. Hello. Good morning, everyone. So, yeah. Firstly, I will present my screen. Tell me if my screen is visible, everyone.
Yes, sir, it is.
Like, okay. And if I change, yeah, it's visible, right? Okay. Nice. So, yeah. So this is my topic: how to lose by making the best decision. And this is a game theory talk. So mostly, I will be giving you puzzles, and I want this to be an interactive one because, like, if you try to solve the puzzles, like, obviously, even if you're wrong, you will like, get to learn something. So I will urge everyone to at least try or like speak up whatever they think in their mind. Like, no one will judge you if it's wrong or right. I will anyway still write solution, and like we just hope to learn something from this talk. Okay.
Yes.
Okay. So obviously the topic is a bit misleading. How to lose by making the best decision. So let's start with that. Like, how can the best possible decision be a mistake, right? So, uh, say you are in a problem, you're stuck in a problem, and you make the best decision according to you based on the clues or like the information that you have on yourself. But eventually, it turns out to be a mistake, and that leads you to losing the game or not solving the problem which you have at hand. Like, my question is it even possible? Like, if you are making the best decision, shouldn't it be the right decision also? But as I like will evaluate in this talk that always the best decision and the right decision are not the same thing, right? So I will show it mathematically. Like, it will be based on some problems, but yeah. So what are the problems that we will face? We will face a cake problem, a pirate, and prisoners problem, and application of traffic jams. Obviously, these topics seem unrelated to each other, but they will make sense once I am done with the talk, right? And the main field of mathematics that we are doing here is game theory, right? So, did everyone understand? Should I start the first problem?
Yes.
Okay. So the first problem that we are encountering is the cake cutting problem. I will discuss the problem and then I will let you people think for some time for some solution, and then I will discuss the answer and the things that we learned from the problem. Okay. So let me explain the problem first. Uh, so Alice and Bob are two people, and their mother bought a cake, and she needs to divide it among them fairly. Right. So first question is, what does fair mean in this context? So can anyone explain what does fair mean?
Like there shouldn't be any impartiality, and like both of them they like get the equal part, like according to me.
Okay. By equal, I think you mean that both of them get half of the cake.
Yeah, like the fair
Fair
probability.
probability of getting the cake.
Yeah.
I mean, probability here doesn't make that much sense. Like, we're not dealing with probabilities here. We basically have a cake. Okay, yeah. I mean, I get what you say. So basically, getting like more than less than equal to. So like what you are trying to say is that probability of say Alice getting at least. Oh, this is visible, right? The writing
Yes, sir.
at least half cake. I think you're saying that this should be one, right? Or
Yeah.
like if you take the volume probability, then like the probability of getting him of the whole cake. It should be more than half or something. Okay, I get you what you're saying. So yeah, that is one part obviously of being fair. The
We can
other
also
part,
say proportionality as being the measure of fairness here. He as Alice might Alice might like something else of the cake, and Bob might like something else of the cake. So proportionality like that.
yeah, yeah. So the first part, okay, that is not proportionality. Proportionality is the first part that we described. That okay, each of them get more than like at least half of the cake, right? The other part which you are describing, that is the more important part. Okay, yeah, I will come to that. Yeah, nice, very nice. Um, let me just grab this. Okay, next. So yeah, I mean that first part is easily solvable. So first part is a proportionality problem that we can divide it because the cake is divisible, right? We can cut it any way we want. Okay. But yeah, the second part is the cake might not be evenly dressed, right? So the example that I gave here, say it has frosting on one side and like it has cherry on other side, but like somebody likes cherry, somebody doesn't like cherry. So even if we like, okay, say this is the cake and this has a cherry on one side and this has some frosting here. So like even if you divide it in half, say these parts are half, my drawing wasn't obvious, but say Alice gets this and Bob gets this, but Alice doesn't like cherry, but Bob likes cherry. So like these are not the fair division, right? So Bob should get this part and Alice should get this part, but we don't know. The problem starts now that we don't know who likes what, but their mother has to divide it fairly. So first we get the things. First one is proportionality, that Alice and Bob should get at least half of the cake. And the second one, to put it formally, it's called envy
Envy
free.
free.
Yeah, exactly. Nice. So envy free is that neither Alice nor Bob should prefer the other piece than their own piece. So like say Alice gets a piece and Bob gets a piece, but Alice prefers Bob's piece more than she prefers her own. Like, do you get it? Like nobody should be jealous of other, right? So my problem is their mother doesn't know about their preferences. So like what does she have to do to make a fair division of the cake? Any ideas?
Half of cherry and half of frosting.
The cherry and the frosting part was
Okay.
a example. Like that might not be the case. Like we just know that the cake is not uniformly dressed. Okay, like not uniform. How do you do it?
Like the only
The
possible
divide and choose strategy. We can like
Can you explain
someone.
that?
Yeah, like we can like say let's say like Alice like she can cut the cake. So she cuts the cake into two pieces that she perceives as being of like exact equal value. And the other person like let's say it will be Bob in this case. So he chooses the piece that he prefers. So Alice like she should be satisfied
Okay,
because
yeah,
by
yeah, yeah.
her own
Yeah, okay, okay,
evaluation.
okay. I get it. You know the right answer. Okay. Anybody else? You knew the question, right?
I had a
you
like
like
idea of it.
generally I guess it's a gamble because and a sad outcome, but since we are trying to find out what she could do in that situation, the first thing would be the cutter strategy and the chooser strategy. One should cut the cake and other should choose the cake, so that way there would be
Yeah.
equilibrium, no case of making a mistake because they both know what they do, like
Yeah. Okay, okay, yeah. Nice.
exactly what
Everybody,
you have written in your I guess that's what you have written on your the first page, NASH equilibrium.
mm, that is an idea of Nash equilibrium. We didn't yet go to Nash equilibrium. This is an example of a mechanism design, like you say. That is a part of game theory. And we are designing a mechanism to for fairness. That is not Nash equilibrium yet because for equilibrium we need some other things. I will discuss that. Like let's not get too ahead of ourselves. Like first let's ask the other people. Did they get what uh, like Samanya and Abhrodip said? If not, I will discuss that. That is the strategy. So the strategy is called I cut, you choose. Uh, So what the mother does is she tells that let Alice cut the cake and Bob will choose his piece. Like first, like Alice will cut the cake in two parts and Bob will choose his preferred piece. And then the remaining piece will be given to Alice. How does it satisfy our like conditions? So obviously when Alice is cutting the cake, she knows that Bob will choose, right? So she will try to cut the cake like in almost two equal parts, like two equal parts according to her, right? So it would be in her preference. If she wants like frosting or if she likes cherry, she will divide that into half part. Yeah, like I think someone said like half cherry, half frost. Okay, that is an equal part, but like it's not always only two things which you can divide in half, but it might be other things. But whatever she likes, she will divide it into half, so that whatever piece Bob chooses, she gets to get the other piece and she is happy with that, right? So she is happy with her piece. We are done with Alice being happy. And since Bob gets to choose between the two pieces, he can obviously choose what he will like. He gets the whole choice. So the piece that he will choose, he won't. So Bob is not envious and Alice is not envious of the pieces because she cut them too equally. So we are done, right? Both of them are happy with this. Nice. I think everyone got it. So the problem, this was a very like old problem. The actual problem is like when there are more than two people, when there are three people, or say when there are more than three people. What if both prefer the same piece? I mean, same piece as in like Alice is cutting the cake into two parts. So my strategy was that she knows that Bob will choose one piece, right? So she will try to make the pieces equal. So that even if like Bob chooses one piece, she will get the other piece, and she should be happy with that. So she gets to cut. She will try to cut them equally. Like, you understand? Like, put yourself in the situation. Say you're cutting a cake into two parts, and one will be taken by another person. So you want to maximize yourself. Like, you are rational. You want to maximize your profit. So you will cut them into two equal parts so that no matter whatever they take, you get the other part and you are happy with it, right? And Bob will get to choose like between these two things. So it's not a question of Bob being unhappy. I think so. That's right. Okay. Yeah. I mean, envy. Okay. Envy as okay. I will define it. How do I get to the? Yeah, envy free is neither Alice or Bob should prefer the other piece than their own piece. Say Alice, okay, yeah. So say this is the cake and we are dividing it into two pieces. Say this is P1, this is P2, and Alice gets P1 and Bob gets P2. So envy free means that Alice won't like, okay, so if I define some preference, like some quantity, some question called preference. So the preference for Alice for P1 should be at least greater than equal to the preference of Alice for P2. That is what I mean. Did you understand? Same for Bob, by the way. Okay, like Bob's preference for P2 should be at least as much for his preference for P1. Okay, I think you understand. So this was a strategy. Children, the procedure is a bit tough. We are not going into it and we are not going into the proof of it. But that is the Selfridge Conway procedure. You can search for it, like, and I will also send the slides so you can just look into it. That is, but like, what did we learn from this problem? We learned that fairness is not always like as easy as it seems, right? Like, okay, can you like say like, I think if you know, then you can leave, but if you don't know, can you try for a strategy like a mechanism design for 3 children for dividing the cake fairly? like the I choose you cut problem won't work here, right? Because like say Alice cuts it into 3 equal pieces, but then say okay, yeah, this is the cake.
maybe could try a bigger process, because cut and choose will not work, but cut, choose, and then cut, choose may work out for 3 people.
Say again.
Just thinking cut and choose might not work for 3 children, but cut, choose, then cut again, and then choose again might work for it. Like Alice cuts the cake in 3 pieces because there are 3 children, 1 by 3, 1 by 3, 1 by 3, and then one of them decides to take up a key. He according to his favorite takes cut piece key. It's not fair, and then they choose again, and something like that, I guess, may work out.
Okay, I mean, it is kind of like that. It's not that easy, but because like after like Bob chooses, so Bob gets his preferred piece, but then Alice and Charlie, they have to cut again. Like Charlie should cut again, and he should cut it into some fractions, so that the other part might be chosen. Like, it's not like you don't cut it into 1/3 part initially. You
I think we can do like one cuts it into 3 parts, and the second goes on and cuts each part separately into 2 pieces. So then we would have 6 pieces, and then there will be a countable preference for the third one. Like third one can now choose, and both the first people who cut the cake initially had their own choices.
no, that is a
How about
problem. Whenever you
how about Alice cuts the cake according to herself in a 3 pieces? These are 3 equal parts. I'm not saying 1/3, but according to Alice, there are 3 equal parts. And then Bob decides 3 equal parts according to him. So he picks up a knife and cuts himself another piece out of those 3, anything else. And then they decide to choose. And Charlie, the third guy, chooses something. Then it's left between Bob and Alice. So Bob have to choose what he have cut, because he have cut that part. So in that way, I am fair. So and then Alice will choose whatever is left, and then there will be, I guess, one extra piece left because of the cutting Bob did. So there must be something around like this.
yeah. You are in the right direction. So yeah, okay. The problem with I think Avinav's approach was that whenever you cut, after you let one guy choose, the second guy's choice, like when you're giving to choose consecutively after cutting, the second choice doesn't hold fairness. Like once you give a choice to one person, he takes the best piece, and the second time you're giving a choice to another, like if both of them prefers the same piece here, because the third guy didn't get a choice really in the cutting, also in the choosing, so his piece might not be fair. That is what I mean. But the procedure is kind of the same that Abhijit explained. It's like the person who cuts first, he or she gets to choose, and then it's a procedure between the other 2 people. They also have to cut in some parts and then have to choose. You can read it. It's the Selfridge Conway procedure. You can search for it and you can read it. Okay. Now, my problem is here we took a easy problem among 2 people, right? So what if they want to maximize their profit? My second problem would be on basis of that. I defined this term rational. I already defined this term fairness. I will define this term rational. What does it mean? Like in a game theory environment, like, or in a scenario. It makes okay. Everyone understood this problem, right? The solution also.
Yeah.
Nice. Second problem is a pirate game. Does anyone know about it?
Yes.
Okay, you also know the solution?
I think it's based on a greedy algorithm, if I remember correctly.
No, actually, but okay. If you think that you know the solution, or if you remember it at any point, I will let other people try. Okay.
Okay, sir.
So the problem statement is there's a group of pirates who found a treasure of 100 gold coins. Now they need to divide it among themselves, right? So the proposal division is that the most senior pirate, he will propose some kind of a division. Say we are taking 5 pirates at this case, A, B, C, D, E. These are the pirates. And say A is the most senior pirate. So he proposes some distribution. Say everybody gets 20 coins each. Okay. If the pirates like, okay, let me show. Okay. So if the proposal is accepted, okay, obviously after that a voting is done. And if the proposal is accepted or if the vote is tied, then the coins are divided according to the proposal. But if the majority votes no, the proposer is thrown overboard, and the next thrown overboard, by thrown over I mean he's just killed, and the next senior pirate makes a new proposal. Did you get it? So say, okay, yeah, nice. So again, if A, B, C, D, the proposal that I explained previously, if everybody gets 20 coins and say A is the most senior pirate, right? If C votes no, D votes no, and E votes no, so it's 2-3 vote like against the proposal. So it is B. Now B will propose a division among B, C, D, E, and this cycle goes on. This continues until a plan is accepted or there is only one pirate left. Okay. Now, there are some assumptions which I will state. Firstly, the pirates are rational. That is, they pick actions to achieve their most desired outcome. That means, what does that mean? Say, if someone is rational, say I am rational. Okay, that means that my decision should be based on maximizing my payoff. Which means if I can get my money, then I will try to get it as much as I can. That is what the pirates want in this case. They want to get as much money as they can. Their decision will be based on that. Okay? That is called being rational. Yeah.
Even if the senior most person's proposal is matched, then also the second most senior will count him in the division as well, right? Or he will be not included in the division.
Wait. Say again. I didn't get you.
Like say A's proposal was discarded, so will B make a proposal which gives A his share also, or they will just discard it?
No. When A will give the proposal whenever he is a senior, like he is a senior right now. So
Yeah.
if A's proposal isn't accepted, he will just die. And then B will give a proposal to divide it among these 4 people, B, C, D,
Okay.
and E.
So now they will divide among 4 only.
Yeah, because A is being killed when his proposal isn't accepted.
Okay.
Okay, nice. Now, obviously, the first priority is for every pirate to survive. And one given survival, every pirate wants to make as many coins as possible. Okay. And each pirate would prefer to throw another. Okay, so this means that say A proposes a division of say 25 coins each to B, C, D, and E, and A himself gets 0. Okay, so in this case, B, C, D, E, and first and third point, same thing. Third points, yeah, third point just says that survival is the first priority. The second priority is being rational. Yeah, this first point I just gave as I wanted to give the meaning of rational. But the rationality comes after the survival. So this has the first point. That is what I wanted to say in the third point. Okay. So you can take the third point as like the priority, on the first point as being rational. Yeah, so what I was explaining the fourth point. Fourth point is that say A proposes a division that B, C, D, E gets 25 coins each. They will still kill A because the best possible decision for B, like the worst possible decision for B is 25-25 each, right? Like that is the, say all the pirates are like very trustworthy among themselves and they want to divide their coins equally. So if A proposes this, they will still kill A. They won't accept their proposal because even B is very trustworthy and B will divide the coins between each. So my point, the fourth point being, if they have the same outcome with killing a person, they will kill the person. So for them, again, killing holds more priority than not more priority. It is being that if they can kill and get the same payoff, then they will kill. So you can say that they are bloodthirsty. Like as in. And the fourth point being, the pirates don't trust each other at all. This point essentially means that forming any agreements, say you can kill one and then we will distribute among themselves and all, like these are not possible. Say B and C forms an alliance. That is not possible because nobody trusts each other. Okay, you get the assumptions?
Yes, sir.
Now the problem
Sir,
is,
even sir, 1 second. You said
yeah.
even, they don't trust each other, but even if they try to form an alliance, B will still get killed because B and C together will just have 2 votes and D and E will have 2 votes again. So it's tie and then
Yeah.
B will get overthrown again. It's
No,
the
no, no, no,
same.
no. Tie, in case of tie, the proposal is accepted. Okay, let's I showed here. In case of tie, if the proposal is accepted or the vote is tied, the coins are divided according to the proposal.
Okay, I just thought if they are tied, they are also overthrown.
No, 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 no. If the majority is no, only then the proposal is thrown over. Okay.
So, sir, can we not make a bribing proposal? Like, say we just exclude A made a plan which A wants 3 votes at least to,
Yeah,
or 2
A
votes.
wants 3 votes. A will obviously himself will vote for his plan. He wants 2 out of B, C, D, E.
2 out of B, C, D. So now he can just give 0 to D and E and split the 100 points among A, B, and C.
Yeah, he can do that. So like you're saying, he will get 34 himself and some 33. Yeah, right, something like that, right?
Yeah. So now, like he should win the vote.
Yeah, he will win the vote. But you miss this point, that the third point. Given survival, they want to have as many coins as they can. So if there is a chance, if there is a chance that A gets more than 34, he will try for that plan. Obviously, he can get 34 and this is a valid. Okay, you can say that 34 is kind of the lower bound. Because if he gives something like that, then, okay, it's not even the lower bound. Say if there is a possibility that D can get more than 33, staying alive. Like if he kills A, then he kills B, then he kills C, then if he can get more than 33. Okay, yeah, that is a possibility, right? So like, okay, say that, then D will vote no, because if he kills A, then he kills B, then he kills C. So there would be only D and E left, and then D can propose a plan so that, let's say that he can take 100 coins and then E will not get anything. And that plan will automatically be passed because D votes 1 and E votes 1.
Yeah, but so that's why I said B and C should form, like A should bribe B and C, not D and E, because D and E are the ones who will be winning at any cost. Like
Yeah, but again, B and C can also kill A and then they can divide 50-50 among themselves. So they are getting more than 33, right?
But when B and C would be deciding, then D and E will also be there, right? So they would want to be making the they won't be the only party to vote.
Yeah, but even if they vote together, it is 2. And if they vote no, then it is 2. And in 2-2, the vote is tied, so the plan is followed.
Oh, right.
Right. So the problem is, that say we are considering 5 pirates right now. So what proposal should the most senior pirate make so that it is accepted while maximizing his own payoff? Again, I took Alice, Bob, Charlie, David, and Eve. A, B, C, D, E. Okay? These are the 5 pirates. A can't remove B, C, D, E. By remove, what do you mean by remove? Killing? No. You only will be killed if you are giving a proposal. You are the most senior pirate, and you are giving the proposal. And your proposal, the majority votes no. Only then you will be killed. Okay, you can't kill the other people. Okay, let's try to think about a problem. Okay, yeah, I mean, I already discussed these.
I can't
Uh,
induction, like try to like work with small cases and see what happens.
Say again, what?
Like I am saying, like if we can like work with small example and then like see like what happens.
Yeah,
Even like
exactly.
idea what happens.
That is what we will try here. But yeah, okay, come on. I think someone typed something.
Maybe there won't be just one single solution here, and we have 2 or 3 scenarios of solutions. We could try to go through backward induction. When only 2 are left, means David and Eve.
Yeah,
Then
exactly.
David will
Yeah,
propose,
okay.
so Eve will.
That approach, that is the exact approach that we will try. Okay.
Yeah, and
Just
using it, I think 98 will be the best.
yeah. Okay. Nice, sir. Okay, just Kamlesh. Yeah, once he is killed, he's out of the relation. Yeah, because they are killed. Yeah. So yeah, we will try the backward induction process because the pirates will always look to the end of the line, right? Like to what they're getting. Like so, it's logical to say that when D is thinking or when E is thinking, they will think when everyone is killed, what do they get? And if A proposes a better solution than that, only then they will accept the solution, right? Because they are rational. They know how to think. Whatever. Okay. Yeah. So our solution will be backtracking. So what is the last case that we will consider? Like what is the first case that we will consider in this case scenario?
So we'll first consider the case, then the Charlie, David, and Eve case, then the Bob, Charlie, David, and Eve case, and finally
No.
the
What is the
Alice
first case?
case.
What is the first case?
Alice
Sorry, I
case
didn't get
or
your first
the
case.
means I am the
No.
first
In the
David and Eve.
backtracking scenario, what is?
Yeah. So the first will be the but David is 100 and get 0 stored in the side.
Your voice is cracking a lot. But okay, yeah, I think I get what you're saying. But your voice is cracking a lot. I mean, I don't know if it's only for my side or it's cracking for everyone. I get what you're saying, though. It's all right. So yeah, just to answer everyone else. So when Alice should be thinking, he should be thinking like to the down of the line, like what he should offer David or Charlie, like not David or Charlie, sorry, D or E. So say like they should agree to the proposal, right? He needs the maximum votes, like he needs 2 votes from all the other 4. So he should think about offering what to whom, and like they will accept the votes. So yeah, the last case is obviously when you take only Eve survives, but it's not possible. That is what I've written here. So why is it not possible? Because we take a case before that and we see that before just E exists, there is D and E, right? D has to be killed for E to exist alone, right? And D can only be killed if his vote has a majority no. But that is never possible because he will obviously vote yes to his own vote. And even if E votes no, that is 1-1 and that is tied. So David will never be killed, right? And David's plan, whatever David's plan is, even if E doesn't like it, it will be followed. And David knows that. So what will he do? One person can vote to own proposal to. Yeah. Everybody votes for the proposal. So what will David do? David knows that whatever he is proposing, that is being accepted. So he has no risk of dying. David can't die. Dying is not a risk for him. So what I said in the third point is, given survival, one will try to maximize his payoff. So we are taking the case when only D, yeah, exactly. We are on only D and E are alive. So David will take all the 100 coins and will give nothing to Eve. And even if Eve doesn't agree to it, this plan will be passed because the voting, the voting goes 1-1 and the proposal is accepted. So Eve knows that if David is the last one to survive, she will get nothing, right? So she doesn't want to do that because Eve is also in no risk of dying. Eve doesn't want this to be the case where she gets nothing. She wants to get something. So she will never let like the previous person die. Who is the previous person? Say the C, D, E. So when this scenario was there, Eve will never let C die, so that it comes to the scenario where only D and E are alive and she knows that she won't get anything. She will try to remain in this scenario, right? So she will vote accordingly when C gives a proposal. Now, what about Charlie? Charlie obviously sees this and realizes that he could use Eve to his benefit. How does he? So, like, Eve will get nothing if he dies, right? And he knows that. So, what he will do is he has to give something more than nothing. So, like, to Eve to gain her vote, right? Because if I said that before, like, if he gives nothing, yeah, exactly. So, if he gives nothing to Eve, what is the problem? Like, say, Eve will anyways get nothing. And even if he gives nothing, so in that case, for Eve, it is the same, right? Even before Charlie dies, she was getting nothing. And if after, yeah, exactly. So she will prefer to kill. So Charlie needs to give Eve something, which is to say rather 1 coin to secure her vote, right? So Charlie's proposal is that he will give 1 coin to Eve and take all 99 for himself. What will happen is he secures Eve's vote, but then obviously David will say no, but Eve will say yes because she is getting something. And if Charlie dies, then she is not getting anything. So she sees a benefit and she says yes. Proposal goes to 1 and this is accepted. But like, do you recognize who is the victim here in this case?
David.
Exactly. So can you tell Bob's strategy?
B will not let B die.
Yeah, exactly. He will not let Bob die, right? But okay, yeah, that is something that you understood, that he will never let Bob die. Nice. So what will Bob do? Obviously, he also sees all these scenarios getting played. So what will he do?
He will try to give 1 coin or like something to like D to get his vote. Like similar to that of C strategy to get to.
I
Give
guess
1 to
Bob-
C.
I guess Bob would
But
target-
if he gives 1 to C, then C.
I
Wait.
guess Bob would
What?
try to-
Let me answer one. Yeah, Abhradeep, say again.
Yeah, I was just saying when there will getting into Bob's head, Bob's thinking will be he will try to get to David and try to tell him ki if Bob is killed, Charlie will try to take the most and David will get nothing. In so that way, so he'll try to get to David ki I will give you something, 1 gold coin to secure his vote, and completely ignore
Yes.
Charlie because he knows that Charlie won't vote for it and try for Eve.
Yeah,
maybe.
exactly. Yeah, exactly. So Swanshu, I think you're right. Yeah, exactly. Because he just needs 1 vote, right? So he will just give. He knows that David is not getting anything. So, and he just needs David's vote. So he will just give David 1 coin, right? Because he needs David's vote. And if he dies, then David gets nothing. obviously Charlie won't accept to it, because if Bob dies and Charlie gets 99 coins and he is not getting, so Charlie will say no, and he is not giving Eve anything. Eve will also say no, because if Bob dies, then Charlie will give her 1 coin. So they both will say no, but then Bob will say yes. Sorry, David will say yes, which is enough because he secures a 2-2 vote and his proposal will be passed. Right? And he gets to leave and he gets 99 coins. So that is him getting maximizing his coins while getting to leave. This is Bob's scenario. So now, can you tell me what Alice's thinking will be? Like, the main problem was with Alice, right? So what is Alice's thinking?
So now,
Like
So
one
Alice
one
will
to
try to
either two of them, and like she will get
will
all
try
90.
to Alice would try to target Charlie and Eve, because Charlie knows Bob
Yeah.
will give him nothing, and then
Yeah,
there's
exactly.
Eve, knows
Yeah.
ki
So
when Bob is
not
there, he will get nothing.
yeah, it's just not it's Alice. Alice knows that if she dies, then Bob will take 99 for himself and give 1 to David, right? So in that case, Charlie and Eve are not getting anything. And yeah, exactly. So Alice gives 1 to Eve and 1 to Charlie and takes 98 for himself. Exactly. So he sees that these people are saying no, and so this is his proposal. In this proposal, Bob will say no, because if Alice dies, then he will get much more than 0. But Charlie will say yes. David will say no again, because David gets 1 if Alice dies. Bob gives him 1. And Eve will say yes, because she knows that again, if Alice dies, then Bob will give her nothing. So she will say yes. Now, obviously, this yes will be like they're getting 1 instead of nothing, but it's enough to secure the vote because it goes 3-2. And the proposal accepted, and Alice gets 98. So this was the thing. Like we were discussing initially that I think someone said that Alice should get 34 and divide it into B and C, 33. But yeah, he can get much more than 34. He can get 98. And he will obviously try for that. So the recursive pattern is noticeable, right? Like this is based on parity. Like whenever you are in an odd parity, you will give everyone of your parity 1 coin and take the rest of yourself. And the even parities will just get nothing. Again, when you are even parity, you will get everyone of your parity 1 coins, and the odds will get nothing. And that is, you can see why that is the proof. You can, I think, prove it formally. Now you got the backward intuition. It's basically an induction. It's a backward induction. Yeah.
Yes,
Nice.
sir.
Nice. So, yeah, you can watch this generalized video. Like, what is the common thing between the 2 problems? That is the question. So, first problem we obviously saw about what's being fair. And the second problem we saw what's being rational. Right. These terms are related in some way. Okay, Alice can also give BD1. Okay, yeah. He can give, okay, the question is that he can give Bob 1. Alice, B, C, D, E. Yeah, I think the question is he can give Bob 1 and what else? Sorry, the message went off. Yeah, Bob 1 and David 1 and C is 0 and here 98. Yeah. Can anyone say what is the problem with this?
Bob will not accept it.
Yeah, Bob will say no.
He can get
No, because like
99
he knows
coins.
like
Why
he can
will he
like,
say just to
and
1
they
coin?
will also not accept because
Yeah,
like he
even
can't
David
die
will
with
say
her.
no, by the way. Because
David will
if
also say
Alice
no.
dies, then Bob will get 99 coins and David will get 1 coin. So David is anyways getting 1 coin. He will want to kill Alice. And even Bob will say no because Bob gets 99 coins once Alice dies. The division is this. So Bob will also say no. And Charlie and Eve will also say no because like they're not getting anything anyways. So Yeah, it will go 1-4 and he will die. Yeah, so my problem is the fair and rational things, these are related. So what do we have to do? Okay, I wrote it in this. How yeah. But like the fair and rational things are related in some scenario, like as in say when someone is dividing, they want to be fair to themselves. But in this case, we saw that being rational means seeing way ahead than what you can do yourself, right? So even when we generalize the cake problem, it gets a bit complicated, and you have to see a lot ahead to decide your like decide what you have to do right now. In this case, it means that whenever you're rational, you are maximizing your payoff. But in that case, the other people are not getting much, right? So when Alice is rational, all the pilots were rational. But in that case, Alice is getting 98. And this, what was Charlie is getting 1, Eve is getting 1, but these people are getting 0. So this is not really a good strategy of dividing. Even if all of them are very rational and logical, this is not a good way of dividing, because Alice, being the senior, can take the most to himself and everybody has to vote yes. Being rational is not always a solution. So what we need is an equilibrium where nobody should divide, right? So now my the defining topic of the talk is Nash equilibrium. What does it mean? Firstly, the idea of an equilibrium is the thing that we did in the last problem, that A has to predict what D and E does, then has to predict what C does on basis of, actually, firstly C has to predict what D and E does, and then B has to predict what C does, and then A has to predict what B does. Okay. But in, say, a 2-player game, say as in chess or something, say there are 2 players, P1 and P2. Yeah, exactly. So if P1 has to predict what P2 does, P2 has to predict what P1 does based on what he does, and like this goes on. So we need an equilibrium. That is the point. We need a stable equilibrium. And this idea is called a Nash equilibrium. The main thing is nobody wants to change their decision. Say P1 made a decision, say S1. Say S1 is basically a strategy followed by P1, and P2 made a strategy S2. So the strategy set that we are using here is S1, S2. And even if P2 hadn't used S2 and P2 had used any other, say S1, S2 dash, where S2 dash is different from S2, P1 wouldn't have changed his strategy. Like the payoff that P1 is getting from S1 is like more in all of his other strategies. Say like I will explain it in the next example, but the intuitive idea is that I take a decision and I won't change my, once you make the move, you can't change it. No, you can change it. It's not about chess. I'm not saying about chess. I'm saying about a game. When you have different strategies, you will choose a strategy based on which your payoff is maximum. Okay, let me actually explain. Yeah. So the Nash equilibrium is that no player can improve their outcome by changing their decision alone. So say a mathematical formulation is there are n many players and the ith player follows strategy SI, then the payoff for the ith player following any other strategy other than SI is less than equal to when it follows SI. Say if I define payoff for the ith player as UI when SI is following, when the ith player is following SI and the other players are following some other thing, say SI -1. Yeah. Say the strategy is equilibrium and no player. Hey, where did your message go? I just saw a message. I don't know, some glitch. Yeah, but yeah, I think what you're trying to say is yeah, it is in equilibrium when if player I just by changing his own strategy can't benefit, say SI, this thing is greater than equal to UI SI dash S minus.
So what is
This
this
is
UI?
yeah, UI is okay. Yeah, I am explaining this. This is basically the payoff or the benefit gotten by the player I. So the gain of player I by following a strategy SI is greater than equal to the gain of player I by following another strategy SI dash when everybody else keeps the strategy same. This is strategy of everyone else. When this is same, when this is same and only the SI one is changed. Okay, let me use another color. I think that would be better. Yeah, use this color. So see, this one is changed. It goes from SI to SI dash. So that means the player I is changing his strategy, but everybody else kept the strategy same, which is S minus I. I just represented with S minus I. So when nobody else changes the strategy and just the ith player changes his strategy, then his gain won't improve. It's greater than equal to, say, when he was following the previous strategy, it was greater than, the gain was greater than what he is getting by changing his strategy. So what I mean to say is he has no incentive to change. He doesn't want to change his strategy because he won't get anything extra out of changing his strategy.
Well, sir,
Yeah.
expecting a symmetric situation, shouldn't we actually compare UI S I dash and S minus I dash when every other person is also taking the same different strategy?
Oh no. This the equilibrium, state of equilibrium is when this holds for every player I. Okay, wait. Yeah. Yeah. This equilibrium is when this condition this holds for every I.
Okay.
Then does it make sense? Like no single player can change his strategy and get benefit from it, and that is true for every player.
Yes. So they actually know that other person will do the same strategy, the same best strategy that I was doing.
You don't know what other people are doing. That is the problem. So you never know what other people are applying, but you just know that you can change your strategy, but you won't get anything. So you have no incentive to change your strategy. Like we don't know what other people are doing, but whatever they are doing, your strategy benefits you the most. So you won't change. And that is true for every. Yeah.
And so if you have not chosen yet, so like if two strategies are granting us the same benefit, then we can have the same probability of choosing anything out of it.
Yeah.
Right.
You can make it as a set, but I am saying that this is a state of equilibrium. So this this SI comma S minus I, this is a state of equilibrium. Now this SI, there might be cases such that this is equal to some UI. Okay, let me again choose another color. Yeah. This might there might be the case when this UI SI dash S minus I. This might be the case. So there are two strategies, SI and SI dash, which are giving you the same payoff. So you can choose in either one of them, but I'm saying that both of them are state of equilibriums. I'm just defining what a state of equilibrium is.
Right.
And this equilibrium is basically called a Nash equilibrium. Now, obviously, this is a bit formal language, Blue. I will show you what it means in the next. Okay, yeah, Kamlesh, can I get back to you after I show the next problem? I think it will be a bit more clear to you then. Okay. Okay, yeah, nice. So now, did you understand this part that nobody has the incentive of changing their own strategy because they are not getting benefit from it, right? Like whatever they're following right now, that is giving them the maximum benefit. If they change the strategy, they won't get any more benefit than this. Did you understand this part? The formal language one, I will get back to you in a moment. Thanks. Yeah, we are also a bit late, so let's just make it a bit fast. Yeah, so like, what if there? Okay, the classic problem to explain is the prisoner's dilemma. I think many of you have heard about it, but we will try to explore this in a Nash equilibrium state. So the problem states that there are two suspects arrested, and they're placed in separate interrogation rooms, and they don't have any means of communication. And the police lack enough evidence to convict them, so they offer each of them a deal. What is the deal? The deal is that they can either confess against the other person, that they know that the other person did the crime and I confess for them, and that is, or they can stay silent. And staying silent is called cooperating, and confessing against them is called defect. Okay? So now the scenarios are as follows. Say both of them cooperate. Both of them cooperate as in both of them stay silent. Okay, wait. Yeah. Both of them stay silent. So what happens is they both get 1 year because police don't have enough evidence to convict them. So they get 1 year. Makes sense. If say one confesses and the other stays silent, then the person who confesses, he goes free because he became a police informer and he confessed for the other person. And now the police have enough evidence for the other person. So the other person gets the maximum sentence because he stayed silent and he didn't say anything for them. So he gets 20 years. And the person who confessed, he goes free, becoming a police informer.
Is the decision
And if
simultaneous?
what?
Is the decision simultaneous?
Yeah, that is the change from the Prider's problem. Yeah, I will tell you. Yeah. So I told, I think here, yeah, the decisions are independent and one will inform of the other decision once they have finalized their own. So they are making decisions, but they don't know what the other person is saying. This is like not same to the pilot problem where they knew what the other person is saying before they made their decision, right? They happened sequentially, and here it's happening simultaneously. So yeah, and if both of them confess against each other, then the both they will simultaneously know. Yeah, they will simultaneously know, and they will both confess against each other. So they both receive some sentence that is more than what they will get when they are silent. But yeah, they have proof now. But both of them again also confess against each other, so they helped the police. So they get 5 years each. They know the consequences. Both the prisoners know the consequences. So what do they do? That is the problem. So the payoff matrix, I can say it like this. If both confess, wait, where is my pen? Yeah. If both confess, then the both get 5 years each. If one confesses and other remains silent, then the person who confesses goes away and they get 20 years and you get the scenario. So what is the best decision? Like, what is the acceptable decision here?
The optimal should be like both of them like they remain silent.
Yeah,
But
exactly.
Yeah.
Exactly. Both of them remaining silent. Yeah, exactly. Fourth one. So both of them remaining silent is the best decision because they are getting the least jail years, right? 1 year, 1 year. But
Yes.
is it a Nash equilibrium?
No.
No.
Exactly. Why not? Because say prisoner A doesn't know what prisoner B will choose, right? So say prisoner A chooses to remain silent and prisoner B confesses. In that case, A will get 20 years instead of 1 year. So in like given another strategy for B, like okay, prisoner A will remain silent only if he assumes that prisoner B will remain silent, but that might not be the case. He doesn't know prisoner B's decision. So prisoner B might confess and it goes for 20 years instead of 1 year. In that case, he is in a loss. He won't ever try to remain silent because he doesn't know what prisoner B will do. What is the Nash equilibrium in this matrix?
They both
The
confess.
5 years and
They both
5 years
confess.
both confess.
5 years
and
both
both
confess.
get 5 years in the prison because Nash
Exactly.
equilibrium says both players can change the decision as one cannot get a better result.
Exactly. So this is a Nash equilibrium. Why is this a Nash equilibrium? Say if he changed his decision. Okay, like say just for prisoner A, we are looking for prisoner A. Prisoner A confesses and prisoner B also confesses. Now, if prisoner A changes his decision, say if he stays silent, then he suffers for 20 years instead of 5 years. So he is better off in 5 years. Similarly, the same for prisoner B, he is also better off in 5 years than 20 years. Like this thing and okay, yeah, this thing and this thing. If he confesses, then he gets 5 years, and if he changes his decision, if he remains silent while A takes his decision, like sticks with the decision, so he gets 5 up to 20. And the same thing is when say if A remains silent, so the prisoner B gets 0 years, and if he changes his decision to remain silent, then he gets 1 year. So prisoner B is always better. Similarly, as it is symmetric, it is same for prisoner A to confess. So both of them confessing is the Nash equilibrium. That is what I explained here. The rational choice is that both of them confessing, because that is better than the alternative, and that is the Nash equilibrium. But we miss the obvious part. Nash equilibrium is not the best scenario to opt, right? Because it's 5 years. Both of them are getting 5 years, and if they both remain silent, then they would get 1 year each. So Nash equilibrium, even though it is an equilibrium, it's not the best scenario. But then there is a high risk factor, so they won't ever go there. But in following the rationality part, right, they ended up being worse. That is what I wanted to show. So yeah, we can modify it. Say, what is the use of the better situation? Say when we are, this is when the prisoner 1 and prisoner 2 are given the choice once, then they will use the Nash equilibrium, right? But say if they are not offered this once, but they are offered this repeatedly, say some many times, say n many times, but none of them know what n. So you can say that they just offered it uncountably many times. Not uncountably, it will be countable. Right? Okay, they'll just offer them infinitely many times. If the same choice is offered to them infinitely many times, what is their approach? Do they always opt for the Nash equilibrium? Because they're always getting 5 years each.
No.
After some time, they will know, right, that Nash equilibrium is not the best thing. We can both go for 1 years each, and there are different strategies that you can follow. And there is this video which employs this when it the prisoner's dilemma is employed as a tournament, not as like a single choice. The same choice is being offered repeatedly. So yeah, I will send this slide. You can watch this video. It's a nice video. And yeah, it has many other applications. Say this occurs in every decision, right? Like every you and say other situation, other player have the same decisions, and both of you, if doing a thing, gets caught up. It's basically a high risk, high reward situation. I think you encounter this many times. High risk, high reward. Every high risk, high reward situation can be expressed as a prisoner's dilemma. And I think you get that like most times. So did everyone understand this? And like, okay, if any questions, like I think Kamalesh, you got the payoff part which you were talking about earlier, or I can explain it once. Oh, you got it. Nice. Anyone else? Any questions? Oh, no questions. Nice. So let's expand on this prisoner's dilemma. We will try people having different initiatives, but okay, yeah, right. Instead of 2 people, we will have multiple people. We cannot change. Instead of 2 people, we will have 1,000 players. So we need a problem for that. And I will go on to the Brace paradox. I don't think anybody knows this, right? Does anybody know what the Brace paradox is? Nice. If nobody knows, it's good because then I can explain it. Yeah. So yeah. Now this is a bit calculated. Let's do it. So this is a story of 2 roads, and we have a road network. You can see the road network, and we have to go from the start point to the end point. There are 2 symmetric roads, one which goes from point A and one which goes from point B. The point A takes the time. Okay, this T represents the traffic. See, the number of traffic is basically the number of people taking this road. So say if there are let's say there are 4,000 drivers in total. If all 4,000 drivers go through this road from start to point A, then the time taken will be 4,000 by 100, that is 40 minutes. So the time taken from start to end following this route would be 40 plus 45, 85 minutes. If all 4,000 drivers are going through this point A route, right? There is a similar, not similar, same route from point B, and it's just reverse. The first from start to point B takes 45 minutes, and from point B to the end it takes T by 100 minutes. Everybody got the model? I can't follow the chats here for some reason.
Yeah, we got.
Yeah. Okay. Yeah. Nice. If you got the. Okay. So yeah. Now let's identify the Nash equilibrium first here. So let's take. How do we find the Nash equilibrium? So let's take. I will explain it. Okay, like we are a bit short on time. So let's take there are A many drivers going through this point A, and there are B many drivers going through this point B. Right. So the time taken, like okay, I mean, I think you are you can understand that these 2 are symmetric, right? So I can skip the formalism right now, but you can understand that since these 2 roads are fully symmetric, then there is no reason for anyone to defect, to change. Like everybody can choose identical from uniformly from these. Minimize their time. Yeah, exactly. They want to minimize their time. So what is it is basically having that A and B, and when you are adding A plus B, it is 4,000, and you want to minimize A and B. What is the minimum possible value of A plus B, so that like sorry, not A plus B, A and B, so that A plus B becomes 4,000.
2,000 both.
Exactly, 2,000.
2,000.
Nice. It's not this easy to state, but yeah, you can get the intuition. Like if we are 2,000 each, then we are getting the minimum value. So we can say that 2,000 people will go from this, and 2,000 people will go from this. So this T by N is basically 2,000 by 100, which is 20, and this is also 20. This is 20.
So basically both roads will go 60, 65, 65.
Exactly. So both roads take 65 minutes each, and this is the Nash equilibrium. Nobody has any incentive to differ, because if somebody from this road goes to this road, then this will in fact become 2001 by 100, and that will be more than 65, right? Like this plus 45, this will be more than 65. So nobody has, so nobody has any incentive to change. This is a Nash equilibrium, right? That is what I wrote here. So the Nash equilibrium, it takes 65 minutes. Now the paradox is, what if we add a road?
So in this case, the Nash equilibrium is giving a fair result, right? Like
Yeah. It is fair. It is fair. Like because Fair as in okay. What do you mean by fair again?
Like say in the last one, the prisoner's dilemma, the Nash equilibrium stated a condition where you can't go worse, like you can't achieve the worst place. But here we have like a situation where it makes sense. It is even for any newcomer.
Yeah. Okay, yeah. Okay, you can say it somewhat like that. But the payoff is more than. This is the best payoff that they can get, right? Like it is not possible for them to go better than this. Like
Yes,
for everyone.
Every person to be rational provides the same payoff.
Yeah. Everyone is satisfied with this thing. Yeah, that you can say that. Okay, because if anyone changes, the other people will be happy, but like the people going through the more traffic route will not be happy. So okay, yeah, you can say that. But the paradox is, what if we try to add a road from A to B, and consider it's a highway, so it takes, and it has no traffic from here because the road is just constructed, so it takes time 0 to go from point A to point B. So what is the intuition? Before doing the mathematics, let's just say, what is the intuition? Should the traffic decrease or should it increase?
Is it just A to B or both B to A and A to B?
No, it is A to B. But I mean, it is symmetric, right? You can also take both B to A, but in that case, the calculation will be a bit problematic. So let's just take from A to B. Just the intuition. Traffic should increase or decrease when we add a new road?
It should decrease ideally.
I mean, obviously it should decrease, right? I mean, the government always adds new roads. Yeah, exactly. So they always add new road and they want the traffic to decrease. They construct over bridges and everything. So that is the paradox. It doesn't decrease, it increases.
I guess it will
How do we show
increase.
this? Yeah.
I guess it will
But we will show that
increase.
mathematically.
I guess by 80 minutes, I guess the new time would be.
Okay. Okay, let's see. Okay, what is the first thing that somebody does after a new road is being constructed? They travel through that road, right? So what if you take this route? Say only one person, like just a random explorer, he takes this route. What is the time? Firstly, he was obviously traveling through this route. So he is the part of the 2000 drivers who are going to this route. So this part takes 2000 by 100, that is 20 minutes. This part takes him 0 minutes. And this part, there were already 2000 travelers traveling from here and he adds up to it. So
20
it's
minutes.
2001 by 1000. Yeah, it's 20.01, which is basically added to the 40.01 minutes, which is a significantly faster result than 65 minutes. Right. So
Yeah.
he took 65 minutes to travel previously, and now he takes 40 minutes, which he is very surprised, and he tells other people that I found a new road that you take that takes less time for you to go. But here the problem starts. Now, more and more people from this region, they start taking this new road. Okay. Change this. Yeah.
Then from
So
B to
now
N,
what
it will
happens?
increase. The time will increase from B to N because the traffic there increases.
Exactly. So yeah, once more people start doing, time will take much more. Exactly. So what happens is, say everybody starts from traveling this route. So what happens is there are 2000 people now traveling from this route, but here there are 4000 people traveling. So it takes 40 minutes. And the people traveling from this route will take now 20 plus 0 plus 40, which is 60 minutes, if I'm not wrong. Right? Hello? Yeah,
Yes.
okay, yeah. Nice.
Yes, sir.
So, but this is still faster, right? 60 minutes is still faster than 65 minutes. What is the problem? Okay, the problem is the people traveling through this route. What is their time now? They take 45 minutes here, and due to the congestion here, it is 4000 by 100, which is 45 plus 40, 85 minutes. The problem is the people who travel from start to end through point B, they take 85 minutes, while the other people are taking 60 minutes. So even they start congesting through this route. The start to A and then to B and then to the end. This. So now what happens is, now the total time is becomes T by 100 in this route. It becomes 4000. All the 4000 people are traveling through this. So it takes 40 minutes here. And again it takes 40 minutes here. The total time taken is 40 plus 40, 80. 80 for everyone. Instead of 80 for like a few group, 85 for, it's 80 for everyone. And this is the new Nash equilibrium, because now nobody can shift and take a better incentive. Like obviously, if everybody shifts, that is good, but nobody can change his personal decision and take a better initiative. This is the fastest route. So Nash equilibrium shifts from 65 to 80 by adding a new route. And that is the paradox. Adding a new route creates more traffic. Now the calculation is shown here, which it takes 85. Okay. Yeah, I mean, the only other incentive is to travel. That is what I showed here, is by taking this route. If somebody doesn't take this route, what he can do is he can take this route, but this route takes 40 plus 45, which is 85, which is more than 80. So nobody will take this route, the light blue colored route. Everybody will take this long route, start to point A to point B to end. And that is why it is a new Nash equilibrium, and hence the time is increased from 65 to 80. Wait, 80 from the original 65. And what is the way to prevent it? Either you can break the road, or everybody can travel like they were traveling previously, from start to end through point A and through point B, and nobody uses the road from point A to point B. But then again, if nobody uses the road, then there will be this one driver. By removing. But there will be this one driver who will use this road and will travel in 40. What is the time? 40 minutes or 45 minutes, I think. 40 minutes. So yeah, there will be always this new driver who travels through this route, and then there will be again the thing that, okay, if he can travel, then even I can travel, and then other people will travel. So it will always repeat in this new conjunction. So the best way is to break the road. And this actually happened once in South Korea. And when the government announced to break the road, and people were like, the traffic is already so bad, and if you break the road, the traffic will be worse and all. And the government proceeded to break the road, and surprisingly, the traffic was improved. So the paradox works in real life. It also has many other applications. In physics, there is a spring application. There's also the electricity traveling, when the electricity is distributed from a distributor to like every one of our houses. It follows the same thing. If you add a new line, the resistance is the least, so the current travels through that side. But then if all the current travels, it becomes an overload and all. There's a problem. That's a physics problem. But yeah, it follows the same paradox. This is called the Bayes paradox. So my point is, we learn different things from different games, but what we actually learned is that the best idea for yourself might not be the best idea that leads you to win the game. So what you have to think is, what is the best for yourself? Best, it might be for yourself, and it might be for everyone else. everyone else, including you. So you always have to go for this process instead of this. It might be that when you follow the second thing, you are not getting what you would get when you focused on yourself only. But then this will always yield you better results than this. And also, this is the least risk factor. We saw the high risk, high reward thing in the prisoner's dilemma. And this is a Nash equilibrium. Nash gave this as his PhD thesis. His PhD thesis was just 28 pages, by the way. And he gave this result, and it changed game theory forever. You have to take the best collective decision instead of the best individual decision. Okay. Yeah, these are the references, and thank you for the talk. If anyone has any doubts, taking only yourself might lose much more. Yeah, it might. It has a high risk because it doesn't. You're not taking into account the other people's decisions, right? So they can take some strategies or employ something which might result into your loss. If you just calculate your gain, it is again a high risk, high reward. If people work according to you, then you get high reward. If people don't, you get high risk. Yeah.
So like in the road question, if that 45 minutes, if that constant road that provided 45 minutes, if that provided a little less time, say 15 minutes on both ends, like t equals 15 equals 15 there, then it would have provided some another case, like then people would have tried that path. Then the whole scenario would have differed.
Can you explain what part? Okay. Yeah. Okay. Can you explain what part? I will try
Like
to draw here. So
instead
this
of
is start. This is end. This is through point A. This is through point B, and
Yeah,
this is the path. Yeah.
so to start to A, that was t by 100, and to start to B, instead of 45, say there is a 15 second. A and B is 0. A and B is 0, sir.
A and B is 0.
Yes, to A to B, the new road is 0, but to start to B, this is 15 seconds time,
Okay.
minute or whatever. And then another thing, A to end is 15 and B to end is t by 100.
This is also T by 100, right?
Yes.
Yeah. Okay. How many people are traveling?
4,000 only.
Okay. Keep the total number of T total 4,000. Yeah.
So now, like in the last scenario, that the thing that happened was the Nash equilibrium occurred when all the people were going from start to A, then A to B, then B to N. But in this case, the Nash equilibrium won't lie there. So the people would prefer start to be at in 15 minutes, because that's that
Oh
is-
yeah. Okay. I get your problem. So no. The model is designed so A and B are midpoints of the thing from start to end, right? And here it's not the same. This takes 40 minutes and this takes 15 minutes. So it's not really the midpoint. Right. The previous scenario was that if everybody travels through this, it would take 40 minutes and it would take 45 minutes. So it is more likely the midpoint. But here it's not the so. So the model states it like that.
like, so if there were 1,500 people going from that areas, then again it would be 15 second, 15 second.
Okay, yeah. That you can do. 1,500 people. Okay, yeah. 15.
But not like that, like 1,500 going from there and the rest 2,500 going from start to B. Like in that case, you would see that from going to start to A, it will also take 15 seconds. So how can we just decide that from that A and B are midpoints or anything? Because the time taken from going to start to A is dependent on the traffic, right?
No, I think the model states that A and B have to be midpoints of the road.
Yeah. Anyways, like considering this to be a model, so like in this case, Nash equilibrium, will it even exist, or what?
Nash equilibrium always exists. Like the existence is proved. So
Oh,
okay, let's see. T equal to 100. So let's say since the routes are symmetrical, even half the people will travel. So 750 people will travel, right? So it will take you 7.5 minutes and it will take 15 minutes. So that is a Nash equilibrium, which goes from this route to here. It takes you 22.5, and it takes going from this route to here 22.5.
But so considering the road A to B, it will be even less.
Oh, when you're adding the road,
Yes.
yeah, when you're adding the road, it will be less, right? Because one people who can travel from here to 7.5, and he will travel from here to 0,
And
and
at
he will
least
travel from.
if we consider 15 people, then okay, that will be the Nash equilibrium. But if we consider the initial 4,000 people, then this whole timings will differ, right? The
Yeah,
Nash
yeah, yeah,
equilibrium has settled for 20 this for 80 minutes. It would decrease.
yeah. So that is what now the model says, that it will be midpoint. So like you have to take the timings accordingly. Like
Right.
the traffic is based on like that. So like when there are more people travel, it won't be t by 100, right? It would be when more people are traveling, it will be some t by 200 or like that. Similarly, when there are less people traveling, it won't be t by 100. It will be t by wait, it's the time, right? So it will be, oh sorry, sorry, I'm so sorry. Yeah, the more people are traveling, so it will be more jammed. So the timings would be t by 50 or t by 80.
So, sir, we can solve these Nash equilibriums by making some algebraic equations, right? We can equate or we can have the inequality signs so that we can limit how many people can go from all the parts, so that the Nash equilibrium is
Yeah,
achieved.
yeah. A Nash equilibrium can be solved in different ways. In this scenario, it's a bit in this scenario it's easy, right? You can see the Nash equilibrium because it's like clearly divisible. But in typical game theory scenarios, when there are two-player games, you can construct the payoff matrix, and then you can see all the entries in that, and like choose the entry which gives you the maximum uh, payoff, and like compared to all the other elements in the row and the column, and you have to choose that element. So like that is your Nash equilibrium. You can also construct some algebraic limits, and yeah, there are those. You can study game theory or mechanism design for that. That is a
Right.
bit formalism. I didn't cover that in this talk.
Got it, sir. Thank you.
Yes. Anything else? Oh, okay. Then I think we can end the talk. Thank you, everyone. This is nice. Is there
Thank you,
from
David, for the
someone from
wonderful
the
work. Yeah, if anyone has any questions, maybe you can take the questions for 10 minutes and then we can end.
So in the chat, someone has asked.
any good resources? Yeah, I mean, I gave the wait. Sorry. Yeah, this book you can follow, but it covers like the second one. You can follow, but it is a bit of a hard book. Like it is the encyclopedia of like all the game theory things. But then I will prefer that you read. Okay, yeah, you see some game theory course taken in some colleges. Like you can go for MIT, OCWs, or some other colleges, and you can read the lecture notes. They will be easier to understand because they explain the topic. Reading from a book, it's a bit hard. Or you can watch some videos also to create the game theoretic intuition or the formalism, and then you can read the book. Whatever you find is more comfortable for you. Okay.
And so the thing that you were talking about, like for in the prisoner's dilemma, if they were given it the choice of that defy or confess many times, then they would eventually come to the conclusion that
Oh, the tournament scenario.
which one where they defied the Nash equilibrium. They they were given the choice infinitely many times. So will this always happen? Like if they are given the same choice infinitely many times, that they would eventually stop following the Nash equilibrium.
Yeah. That is the tournament scenario that is you're talking, right? So like they are offered the choice more than once.
Yeah.
Yeah. So uh, this actually you can take different strategies, right? So okay, let me
Then
tell. Is there time? Like, can I tell a bit more? Like, I'm asking the limit.
you can go on for like 10 minutes. Maybe.
Okay, yeah. So this scenario, there was okay. Let me tell you a story. This scenario was actually employed. Say, what if we do the prisoner's dilemma not once but repetitive scenario? So there was a mathematician. I forgot his name, but he gave a competition where you can submit bots. Where in a tournament scenario, say I am submitting one bot, say B1, you are submitting one B2, and there are some B and many bots, and they are made like they are put into the simulation of prisoner's dilemma, and they are made to compete against each other. Say B1 versus B2 and B2 versus B3, and like that. And it's a Swiss round, and it was in an effort to find what is the best strategy, and it was found that there exists a best strategy for this scenario, like a strategy which trumps every other strategy. Like people employ different strategies. Okay, like some examples. Say, okay, yeah, let's take the choices as only defect or cooperate. If both defect, then you lose. No. Wait. Yeah, you get the point system, right? If both defect, then it's like 1 year each, and both cooperate. Let's transform that into payoffs. You get the maximum payoff when you get when you are cooperating and the other person is staying silent, and you get a medium payoff when both of you are cooperating, and you get the least payoff when both of you are silent, right? Oh, so no. You get the least payoff when you are silent and the other person is cooperating. Yeah, but you get the scenarios. So it was made as a point scoring system, and people had multiple strategies. So like there was one bot, say BI, which had the scenario that it will always stay silent. Because no matter whatever you do, either I get like this high risk, high reward scenario, right? Either I get highly rewarded or I get highly risked. And it played on the gamble. There was a gambling bot which with 1/4 probability or 1/3, 1/2 probability, it will either stay silent or it will cooperate. But there are different strategies which different bots employed, and there was this one bot which stood up. Now, do you want me to tell the strategy or do you want to guess it for yourself?
Yeah, it would always defect maybe or what? Like
No, always defect was not the strategy. It's a very surprising. Okay, so the bots were categorized as good bots and bad bots. Yeah, always defect was I think in some top part of the bad bots. But the best strategy was a tit for tat strategy. That once I will start with cooperating, and once you defect, I will start defecting. And again, once you cooperate, I will start cooperating. Like once you defect, I will defect, and otherwise I will cooperate always. That is the strategy, and that strategy won. So you can look into this video. I think I will send the slides so you can look into the video. They explained all strategies very in a
all, this
proper
is
way.
Yes, sir. All and this thing is applicable when both the players are not told how many times they have to choose. Like, say if
Yeah,
we have given them 100 choices, we are giving them 100 times, but they don't really know that we will end at
yeah.
100.
Because like if they know that they're choosing 100 times, then in the last time they will choose defect, right? Because defect has the high reward because you are always cooperating. and the other bot will also think like whenever it's 100 times, and you know how many times it will consider into the pilot game, right? You know the last outcome, so you know the second last outcome, and you know the third last outcome, and it will end up being defecting in all the outcomes, and nobody will get anything. That is that is why you don't know how many. That is the strategy.
Perfect, sir. Got it.
I think no other questions probably. So yeah.
And so this was the optimum choice, right? So like infinitely many times, the Nash equilibrium will slowly turn out to be the most optimum choice for both the person.
Yes. Yeah. So this we don't know. I don't know if there is a proof for this, but this scored the best among all the bots that were sent. And even while we changed some conditions, this like some conditions against of this bot, like to say that if it's actually the best or it's just a fluke, it still performed the best. Like it was the best in all the scenarios that we took the cases in. So it's most probably the best, but I don't know if there is an actual proof of that.
Yeah, got it, sir.
I think I'm done.
Yeah. If anyone has any questions. Okay, if not, then thank you, Daibik, for the wonderful talk. And for the others, you can join in at 2 for the Jane Street estimation session. Maybe we can close now.
Okay.
Thank you.
Bye everyone.